today we are going to be talking about thermal physics. Just before we get started, just a little note that this video will actually be covering all of the thermal physics up to ideal gases. So this is just part one of all of thermal physics. So stay tuned for part two, in which we're going to be covering all of ideal gases as well, which are also part of thermal physics. I'm going to be covering the OCR Physics A specification. However, as always, the physics is applicable to all exam boards. Okay, well, let's get started. What we need to talk about first is thermal equilibrium. So in general, energy is transferred from a region of high temperature to a region of low temperature. For instance, if I had a room full of air, let's say, and let's say that maybe I had like a fireplace and a little bit of a fire at one end of the room, then the heat will actually slowly get transferred towards the other end of the room. Now, when two objects are in contact with each other and they're of the same temperature, there's no net transfer of energy between them. So in general, if I had two objects in contact, let's say that I have object A over here, then I have object B just here, they're in contact with one another. They're going to transfer heat until they're both at the same temperature. So the hotter object will tend to get a little bit cooler, and the cooler object will tend to get a little bit hotter. Okay, now how do we actually measure temperature? So you guys will already be familiar with the Celsius scale, which we tend to use throughout our daily lives. If you're in the USA, you would be familiar with the Fahrenheit scale. Now, in terms of the Kelvin scale, though, which is really important because it is the absolute scale of temperature. How do we convert from Celsius to Kelvin? It's actually really easy. All we need to do is add 273. If you want to be really precise, it's 273.15 approximately. However, for the purposes of the exam board, we don't need to worry about that. For instance, 0 degrees Celsius is actually 273 Kelvin, 10 degrees Celsius would be 283 Kelvin, 21 will be 294 Kelvin, so on and so forth. So the Kelvin scale is actually the SI unit for temperature because it's an absolute scale. Additionally, the Celsius scale is actually based on a couple of points, and those are the freezing point of water and also the boiling point of water. So these are not actually absolute. I mean, they depend on pressure, so this is really important. For instance, if I was to try and boil water at sea level, the temperature at which happens would actually be a little bit different compared to if I was to try and do exactly the same thing on Mount Everest. So in order to get away from this problem, we need to use an absolute scale, and that is the Kelvin scale, which is the SI unit for temperature. Okay guys, now moving on to solids, liquids and gases and their kinetic models. So we can think about these states of matter as different states of the particles that make them. For instance, when we have a solid, the particles vibrate in a fixed ordered lattice. So I'm just going to highlight those keywords here. Really important is they're fixed. It's a fixed ordered lattice. Now, if the temperature is increased, the amplitude of the vibration actually increases, and this is really important. We need to say what physical quantity of the vibration increases. Please don't write something like, let's say, more vibrations. So this is just not precise enough, I'm afraid. So this is a no-no, so I'm going to just cross that over. The spacing between the particles is very small indeed. Now, if we have a liquid, the key difference now is that the particles are no longer fixed. So they're vibrating but not in a fixed position. They can actually flow past one another, and once again they're vibrating but not in a fixed position. So in a solid just here, they're kind of like oranges in a crate. They can move about a little bit, but they're fixed within their positions. Not the case in a liquid. Now in a gas, the particles are very, very far apart. So the distance between the particles is very large. They're actually so far apart that they don't exert any forces on each other except in collision. So the particles also tend to move in a random linear motion that we're going to be investigating next. A classical way to actually investigate Brownian motion is with the smoke cell experiment. This can also be demonstrated with pollen grains in a liquid in exactly the same way. A typical setup for the smoke cell experiment will be a microscope, which is pointed at a little smoke cell. Essentially, it's a container, the cell, in which it has some air, and all we do is we inject some smoke particles. We also tend to have a lamp on the side just so that we can actually visualize what is going on. Now if we were to zoom in, we would see something similar. We have all of these particles, and these over here are the smoke particles that we see. So these over here are the smoke particles. Now they tend to move completely randomly. So for instance, you can have a particle which kind of goes here, then goes here, then goes here, then goes here and there, etc., etc. And it tends to move, so the smoke particles are moving in a random linear motion. So this is really, really important. They're moving in a random linear motion. Additionally, the air particles cannot be seen. We only see the smoke particles. Now, what conclusions can we actually make from this? First off, because the smoke particles are moving in a random linear motion, this must be because they're colliding with the air particles which are not visible. So this is the conclusion that we can make from this observation. I mean, if we think about it, let's try and zoom into this. So see if I can zoom in quite a bit, and imagine that we have this smoke particle. If this smoke particle is moving randomly, this must be because they're tiny, much tinier air particles which are also moving in random linear motion. So if this particle is moving in random linear motion, there must be air particles which they're colliding with it, causing it to move like such. So the air particles cannot be seen as well, and the reason for that is because they're a lot smaller than the smoke particles. So those are the two main observations and the two main conclusions of this experiment. So let me just say that this one over here is the conclusion from this observation. So once again, the small particles are moving in a random linear motion. The air particles cannot be seen. The smoke particles are colliding with the air particles, which must also be moving with random linear motion, and the air particles must be a lot smaller than the smoke particles. Okay, we're on to a very, very important exam definition which tends to come up in exam papers again and again and again. So please pay particular attention to this, and that is internal energy. Now, internal energy is defined as the sum of the randomly distributed kinetic and potential energies of all the particles of a substance. So a few particular points. It is the sum, so it's not just the kinetic, it is the sum of the kinetic and the potential energies of all the particles of a substance. So the last bit is really, really important. I'm even going to add the all here, so I'm going to say of all of the particles of a substance. Really, really important. For instance, I have this container of water over here, and each of those particles is going to be moving in some direction, so it's going to have some kinetic energy. Additionally, the particles are going to exert some forces on one another. They're typically going to attract each other. So the internal energy, let's call that U, it's typically given the symbol U, is defined as the sum of the kinetic energies of all of the particles plus the sum of the potential energies of all of the particles. Now let's have a look at a very, very important graph in physics. For instance, if we had a piece of ice and we started heating this up, it will go through some very, very similar temperature changes. First off, we're going to be in the solid phase. So at this stage, the temperature of the ice is simply increasing. Now, because the temperature is increasing in this region over here, the kinetic energy is also increasing. The potential energy increases, but by a very small amount. So let's just say the potential energy increases by a small amount. This amount is virtually negligible. It is due to the fact that when the kinetic energy is increasing, the particles are vibrating with a slightly greater amplitude, and they get displaced a little bit, so the potential energy increases by a little bit more because the particles are just slightly further apart. Now, when we reach a certain temperature, and if this was the case for ice, this will be 0 degrees Celsius at sea level pressure, then the solid will begin melting. Now at this stage, the temperature remains constant, and we can see that the temperature is constant. So if the temperature is constant in this region over here, the kinetic energy is constant. And all of that energy goes into breaking those molecular bonds and pushing the particles a little bit further apart and just breaking them away out of their fixed position. So at this stage, the potential energy is increasing. Why is the potential energy increasing? Well, the particles have been essentially ripped apart from their perfect lattice. So if they were like this between, maybe you could have, let's say one of those particles is now kind of free to move. So maybe it goes here, another one goes here, another one goes here, and they start moving in a slightly more random motion. The whole process then repeats itself. So here we have a liquid. We can see that this graph is increasing. So the kinetic energy is increasing. The potential energy increases by a small amount. So increases by a small amount. Then we have a liquid which is evaporating. When this is happening, we once again have a flat line here, which tells us that the kinetic energy is constant because the temperature is constant. So the kinetic energy is constant, and once again, the potential energy is increasing. In fact, the particles are now pushed really further apart, and finally we have the gas stage, and as the temperature increases, we can say that the kinetic energy of the gas increases. Okay, moving on to specific heat capacity. So what is specific heat capacity? The specific heat capacity is defined as the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. So one way of, in general, defining quantities or units as well would be just to rearrange for them. So we can see over here that C is equal to energy, or the energy required in our definition, divided by the mass and the change in temperature. So the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. What are the base units of specific heat capacity? So this is another question which could potentially be asked in an exam, even though it's a slightly non-standard question. Let's think about it. So we're going to need an equation for the base unit for the joule. So let's pick our favorite equation for energy. Let's say a half mv squared. The half has no units. Mass is in kilograms. V squared is in ms to the power of -1. I'm going to square that. So remember, the base unit for energy is actually kilograms meters squared s to the power of -2. Okay, well, this means that the base unit for the specific heat capacity, I'm just using these brackets to showcase and be talking about the units, will be equal to kilograms meters squared s to the power of -2 divided by kilograms, because m is the mass, and then the change in temperature, which is going to be given in Kelvin. So the units for specific heat capacity are going to be, when the kilograms actually cancel, going to be meters squared s to the power of -2 k to the power of -1. Now, how could we determine the specific heat capacity of an object? Let's have a look at a little experiment. And now let's have a look at a very, very interesting specific heat capacity experiment. This is quite a typical question, and it's an excellent candidate, for instance, for an extended writing question. In this case, we have the following setup. So we have a little electrical cell which is connected to a variable resistor. We could also be using, for instance, a variable power supply, and we also have an ammeter, and we also have some voltage. We have a liquid which has been placed in an insulated container, and we also have an immersion heater. Notice that the immersion heater is fully submerged within the liquid. The experiment will just not work if this was partially submerged. So if you draw this diagram in an exam, please make sure that to draw the immersion heater fully submerged. Okay, now what will our procedure be? What are we going to measure? First off, we're going to measure the mass of the water using a top-down balance. So that's one thing that we're going to measure. We're going to then measure the current I, the voltage V with an ammeter and a voltmeter respectively. We're also going to measure the temperature on set intervals with a thermometer. The time intervals we're going to be measuring with a stop clock. For instance, maybe we're going to measure the temperature every 30 seconds for, for 20 minutes. For instance, this is going to give us sufficient data. Now, to reduce uncertainty in this experiment, we're also going to try and stir the liquid regularly, as the temperature of the liquid will be uneven. Some of the energy may go into the container, and this can be included into the calculations. After we've done this, what we want to do is to plot a graph. Just write this. Plot a graph of temperature against time, as shown over here. Now we can actually use this graph. So we plot our data points, we draw our line of best fit, and how could we use this graph to determine our specific heat capacity? Well, this is where it gets quite interesting. Remember, our specific heat capacity equation is E is equal to mc delta theta, which is the change in temperature. Well, let's do a little bit of a mathematical trick. Let's divide both sides by the time. So if we divide both sides by time, or a different way of thinking about it is, let's introduce power into the equation. So remember, power is energy over time. Yeah. Therefore, energy will be equal to power multiplied by time, and this will be equal to mc delta theta. Just write power properly. So let's try again. P times T. So energy just power times time. And this is equal to mc delta theta. Now what I'm going to do is just rearrange for the power. So power will be mc delta theta divided by time. Well, hang on a minute. Change in temperature divided by change in time. This quantity here is our gradient. So this here is the gradient of this graph, because this is just our temperature T divided by the time T. So delta theta is just the temperature, by the way, so maybe we should just change the label of this graph just to be consistent, assuming we've been measuring in degrees Celsius. So delta theta, the rate of change of temperature, will be the gradient of the graph. So let's just write down that we're going to find the gradient. I'm going to just call the gradient m. So let's write, actually let's call it a different symbol, because we already have an m in this equation which stands for the mass. Let's just call that grad. Okay, well, that means that the power then be equal to the mass times the specific heat capacity times the gradient of our graph. So what we need to do afterwards is just rearrange for specific heat capacity. Specific heat capacity will then be equal to the power divided by the mass times the gradient. However, remember, we've already measured the current and we've measured the amount of voltage as well. So we could really easily find the power. So the specific heat capacity will then be equal to V times I divided by the mass times the gradient of our graph. And finally, let's talk a little bit about specific latent heat. Now, the specific latent heat of a substance is the energy per kilogram required to change its state without any change in temperature. There are two types. There's the specific latent heat of fusion, which is the energy required to essentially melt a substance at a constant temperature. And there's also the specific latent heat of vaporization, which is the energy per kg required to vaporize a substance. The formula for it is actually fairly simple, simply that E is equal to the mass times the specific latent heat. We can actually see where this definition comes from. If we were to rearrange for L, which is the specific latent heat, we're going to find that L, the specific latent heat, is equal to the energy divided by the mass. So we tend to measure that in joules per kilogram. And if we're talking about the specific latent heat of fusion, we tend to call this just LF. The formula is exactly the same. It's just the energy per unit mass. If we're talking about the specific heat of vaporization, we tend to give it the subscript V for vaporization. This will also be energy divided by mass. Okay, now let's have a look at an experiment to determine the specific latent heat. We have a very similar circuit. So we have a little cell. Let's do a little bit of labeling as well. So this over here is a cell. We have an ammeter. And we're also going to connect a voltmeter across our heater as well. So this here is a voltmeter. We have a variable resistor, which just allows us to control the voltage in the circuit. So we have a variable resistor. We have a funnel which is filled with ice. And this over here is our heater again. Now at the bottom, we're going to have a little beaker, and all this does is actually just serves to collect the ice as it is melting away. Now, how are we actually going to do the experiment? First off, we're going to set up the circuit as shown, and we're going to measure the current with an ammeter and the voltage with a voltmeter. We're going to let the heater melt the ice for a set time, which will be measured with a stop clock. Then we're going to measure the mass of the ice that has melted. We have a problem though. Some of the mass that's been melted and is collected in the beaker will be from the effect of the heater. However, some of it would have melted anyways because the room is at, well, room temperature, and if you just leave a block of ice at room temperature, it's going to start melting away. In order to determine how much of it would have melted, or to estimate how much of it would have melted because it's at room temperature, we need a control. And the purpose of this control essentially is exactly the same beaker. The only purpose is to determine how much ice will melt at room temperature and to subtract that from the result of the heated circuit. And this over here is just our control. So let's say we have just a tiny bit of ice that has melted because of the fact that the ice is at room temperature. So essentially we're going to take this mass here, we're going to subtract it from this mass. As a little example, let's just put in some number. Let's say this here was 500 grams, and let's say this one here was 70 grams. Then our mass M will be 500 take away 70, which is 430 grams, as an example. Okay, well, we have the mass that is melted, we've subtracted it, and then all we need to do is use the fact that the energy that we've inputted into the system is equal to the mass M times the specific latent heat. Now our specific latent heat is E over m. Well, just notice that LF, I've not written it quite well. Let me just rewrite this because it's a L subscript F, so let me just be a little bit more clear and make this a little bit smaller. So L subscript F is actually energy divided by mass. We know that the energy is V times I. So all we need to do is multiply the voltage, which we've measured, by the current, which we've measured, and divide that by the mass, which we've also measured. And if we do that, we have our specific latent heat of fusion. Okay guys, so final experiment, and that is to determine the specific latent heat of vaporization. Well, once again, we're going to have exactly the same circuit as before. So we have a cell that's been connected to an ammeter, to a variable resistor that's connected to a heater. Now, the heater will then be placed in the following device, which is known as a condenser. So you can imagine that literally this heater over here is just kind of brought down to this over here. So this is essentially the heater over here. The heater is brought to a condenser. Now we pour a little liquid in there, and then we start heating it up with the heater. As soon as it reaches the boiling point of the liquid, for instance, if this was water, as soon as it reaches 100 degrees, it will start vaporizing. We're also going to have a thermometer that we're going to be using to measure the temperature inside of this condenser. So when it starts boiling, this is actually just a zoomed in version of this whole diagram. The gas will then travel through here. It will condense back to a liquid, and it will be collected in a collecting flask. So we're going to know this device will be this condenser will be able to tell us how many kilograms of the liquid have actually been vaporized. So in short, we're going to take a condenser to collect and measure the mass of a liquid that has changed phase. Then we're going to measure the current with an ammeter and the voltage with a voltmeter. This will once again just give us the electrical power later on that we could use to find the energy. We're going to turn on the supply and heat the material for a time measured with a timer until all the liquid has boiled. I'm going to be checking the thermometer regularly to ensure that the temperature of the material remains at its boiling point. Finally, when we've done that, we're going to use the specific latent heat of vaporization. We'll just write that down over here once again. LV is equal to energy per mass, and this we've found out using the condenser. So we have found this using the condenser, and the energy, well, the energy is just power times time, which of course is V times I times T. So what we're going to do is we're going to find the specific latent heat of vaporization using V times I times T divided by M. Okay folks, well, this was quite a long video in which we've covered virtually all of thermal physics except the ideal gas equations. So stay tuned for another revision video on the ideal gases equations. If you would like to have a look at them now, if you're revising them, I'm going to leave a link for a playlist on individual videos on them in the description of this video. Thank you very much for watching, and I'll see you in the next video.